Okay, let me prove. Again, this is very important. Let me iterate because this is such an important argument. This is very very important. This is P mu P. If we hold two assets in the efficient frontier, with only these two assets, we can entirely recover this efficient frontier. Why is that? Why is that? In order to prove this, we need some mathematics, but here, I want to prove this one only intuitively, only qualitatively, only logically. What if it is not at the efficient frontier? Suppose, okay, this is efficient frontier. Suppose this is efficient frontier. And then we have two assets. Even this one is fine. Okay. What if they are not efficient frontier? Suppose we combine this one and this one. If we point to the, what if they have something else somewhere here? Right? Okay. What if somewhere here? Okay. Alternatively, if we point to the, what if somewhere here? What I want to say is that this is impossible, and this is also impossible. Okay, it is easy to persuade that this is impossible because, well, this red line is the best we can do. So even if we combine any asset, this is because it is best. So therefore, even if we combine these two assets, if we reach this one, then it is a contradiction. This is not efficient frontier anymore. Because the red one is the best we can do, and it is by the definition of efficient frontier, we cannot do better than this one, so therefore it is wrong. Right? So it is wrong. So this is wrong. Okay, so we can rule out this one. But what if this one? This is more interesting case. This is a usual intuition, right? If we have only two assets, and if we combine only two assets, we cannot better than combining like hundreds of assets, right? That's usually true. But actually this is not true. So let me explain this one. So suppose we have this one, efficient frontier, portfolio efficient frontier, and this one, and then we have linear combination this one, which means that we flip the argument. It means that we can use, if we flip the argument, we can use this asset and this asset, and combining this, and we can produce this asset, right? This is logic. Because we use this one and this one to produce this one, then it should be possible that we should be able to use this one and this one to produce this one, right? Right? So if this happens, we can create this one with this one and this one. But what if, okay, then another case is, then, well, this is especially not efficient frontier. So alternatively, we can create some asset over here. Asset over here. Then in that case, well, instead of, if we combine this one and this one, then produce this one. What if we combine this one and this one, right? This one is worse than this one. So if we combine this one and this one, then we should be able to generate portfolio better than this one, right? Somewhere over here, right? Because combine this one, generate this one, combine this one, generate far better one, right? Far better one, right? But that is also wrong because we already know it is efficient frontier. So whatever we do, we cannot beat this one. So that is not possible, right? We cannot combine this one and create something better than this one. It is not possible. Therefore, we proved our argument. Okay, if we combination of this one and this one create this one, creating this one and this one and this one, or combining this one and this one creates much better than that, which is against the definition of efficient frontier. So only consistent arguments that if we combine this one and this one, it should be this one. So if we combine this one, it should be this one, right? So again, therefore, if we combine two portfolio efficient assets, we cannot do better than efficient asset, and we cannot worse than efficient asset. The only possible logical conclusion is that it should be efficient frontier. Therefore, with any two assets in the efficient frontier, we can perfectly recover efficient frontier, right? Actually, this is called two-fund separation theorem. In the economy, we don't need multiple assets. We only need two assets. Any two assets in the efficient frontier. With only two assets, and we can do best. We can beat that one. So that is two-fund separation theorem. Very important. Two-fund separation theorem. Two-fund theorem sometimes. Two-fund theorem. All we need is only two-fund. Well, once we believe two-fund separation theorem, it instantly creates very interesting case. Okay, interesting case. Okay. Let's go over this. On a fine combination of two portfolio at the efficient frontier or set efficient frontier. Any portfolio in an efficient frontier is a fine combination of two portfolio at the efficient frontier. Okay. Now, minimum variance portfolio, which we call MVP, is an efficient frontier, which means that this one, the minimum is always the efficient portfolio, right? And that is a simple logic. So it is up to you. It is very easy to follow. The minimum variance portfolio is always an efficient portfolio. Okay. Now, by the previous argument, suppose that we have three assets in the efficient portfolio. Asset I is in the, suppose we have two portfolio at the efficient portfolio 1, 2. Then by appropriate linear combination, we can create this one. Well, this is strange. Right, again. Right. Here, Ri, right, portfolio return I. By combining, by investing beta fraction in second asset and 1 minus beta fraction in the first asset, we can create Ri. So for any asset, three assets in the efficient frontier, we have this asset. And then suppose asset I is not at an efficient frontier. Not. Okay. What does that happen? Okay, if it is not. Okay. It is not at the efficient frontier. Not at an efficient frontier. Okay. Well, if a portfolio is not at the efficient frontier, then we have to add some noise. Right? We have to have some noise. This noise is very interesting, very noisy. Its noise is independent of R1 first set and independent R2 asset. So this noise is mean. This noise is mean zero uncorrelated error, right? Because if it is correlated, it affects us. So because it is inefficient, so we can just add noise without. So this one is efficient frontier. So this one Ri is difficult. So Ri summation. This is Ri. What we can create this one is by combining this one and create this one, and we can simply add noise to increase standard deviation. We reach here. So for any asset, it is interesting. For any asset, we can decompose that asset with linear combination of the two funded efficient frontier and pure noise. Furthermore, we know minimum variance portfolio is always at the efficient frontier, right? Minimum variance portfolio is on efficient frontier always. So instead of R1, we change it to RMVP. So for any asset is RMVP plus linear combination of minimum variance portfolio and some other efficient portfolio and pure noise. Furthermore, if there is risk-free asset means that risk is zero. So if there is a risk-free asset, it is by definition minimum variance portfolio, right? So if there is a risk-free rate, we instead MVP, we put RF, risk-free asset, risk-free return, because risk-free asset is minimum variance portfolio. So we write this one. Furthermore, if this asset, some asset in the efficient frontier, if we use portfolio called market portfolio, I will discuss more of market portfolio. If we change this one efficient portfolio into the market portfolio, then it becomes this one, and it is famous capital asset pricing model. So if M, some asset, M is some, so in this case, it is not capital asset pricing model as well, not yet. It is risk-free asset. RM is any portfolio in the efficient frontier. And if we change any portfolio in the efficient frontier into the market portfolio, then we have famous capital asset pricing model. If M is a market portfolio, we have a capital asset pricing model. Well, capital asset pricing model is very, well, it is a particular case. We have risk-free investment. Well, it is minimum variance portfolio, and here we, by combining, this is the efficient frontier, and by holding this one and this one somewhere in the best combination of risk-free asset and the inefficient frontier is this one. So we have this straight line. So this tangent portfolio called a tangent portfolio, right? So this green line is actually this one, and the capital asset pricing model. This is a green line, and the capital asset pricing model says that this tangent portfolio is market portfolio. That's the whole point of capital asset pricing model. Okay. So this this straight line is capital market line. This is the efficient frontier that we can generate only with risk asset. And if we have risk-free asset, it is a global minimum variance portfolio, and we can this line. This is the best we can do, and this is the best efficient. This is the efficient portfolio, efficient frontier with risk-free asset. So it is efficient frontier only with risk asset. This is efficient frontier with risk asset plus risk-free asset. And this particularly, which this capital market line tangent, these two efficient frontier meet this point. This is tangent portfolio, and capital asset pricing model says this tangent portfolio is market portfolio. For the detailed explanation of the capital asset pricing model, you can go to any textbook, or Wikipedia has a very good explanation of a capital asset pricing model. In finance, the capital asset pricing model, CAPM, is model used to determine the theoretically appropriate required rate on about asset to make decision about adding asset to well-diversified portfolio. Well, it is very well written, so if you have time, you can read this one. What I want to argue is that capital asset pricing model has very close relationship with mean variance optimization. In many textbooks, explain capital asset pricing model and then mean variance optimization together, but those textbooks do not logically connect those two important concepts. Here I want to hypothesize that capital asset pricing model and mean variance optimization is mathematically tightly related. You cannot understand one thing without knowing the other. Now, in order to refresh our understanding about capital asset relationship between capital asset pricing model and then mean variance optimization, we need to do rules critic. Rules critic is very famous logical critic about capital asset pricing model. Before rules critic, what people did is that, well, they formed the market portfolio. They have some number of assets, and they have risk-free asset, and they combine that, and they create a tangent portfolio, and by connecting tangent portfolio, and they form this relationship, and they indeed find that this relationship hold. Okay, They indeed find that they actually did this, that, not market, this tangent portfolio. They indeed find this. So for some asset, what they empirically found is that this expected return, okay, if we put expectation each side, this goes away. So what they find is, well, if we have high beta, then we have a high expected return. They found. Those researchers found, and they argued that, well, I found a linear relationship between this one and expected return of this one, then CAPM is right. But Roll said that this is totally wrong. Okay? The linear relationship between beta and expected return should hold tautologically. By the construction of the mean variance portfolio, this is always increasing function of this one. Expected value of this one always increasing function of this one. So using the data, if you find the linear relationship between beta and expected return, it doesn't say anything. It automatically comes from mathematics. Mean variance total. Any mean variance efficient portfolio RP satisfies the CAPM equation exactly like this one. A portfolio is mean variance efficient if there is no portfolio that has a higher return and low risk than those fully efficient portfolio. Mean variance efficiency of the market portfolio equivalent to the capital asset pricing model equation holding. This statement is a mathematical fact requiring no model assumption. Okay, given a proxy for the market portfolio, testing the CAPM equation equivalent to testing mean variance efficiency of the portfolio. So if we have a mean variance efficiency is right, if a portfolio is at the efficiency frontier, capital asset pricing model should hold always. So therefore, this kind of capital asset pricing model is tautological if the market is assumed to be mean variance efficient, right? So again, to summarize, if market portfolio is on the efficient frontier, then capital asset pricing model holds mathematically, tautologically. So it doesn't say anything. Then the whole question is whether market portfolio is on the efficient frontier or not. If market portfolio is on the efficient frontier, we don't need any test. Capital asset pricing model holds directly. However, if a market portfolio is not on efficient frontier, maybe capital asset price relationship CAPM does not hold. However, there is a second challenge. The point is that the market portfolio is unobservable. We don't know what is market portfolio. If we assume market portfolio is in the efficient frontier and we mathematically consider any efficient frontier, capital asset pricing model holds tautologically, but that doesn't say anything. It is not science. In order to test whether capital asset pricing model is right, we have to find the market portfolio and we have to prove that market portfolio is on the efficient frontier. Unfortunately, it is impossible, almost impossible. The market portfolio in practice would necessarily include every single possible available asset, right? Including real estate, precious metal like diamond, stamp collection, jewelry, that anything with any worth. The returns of all possible investment opportunities are unobservable. Okay? So from the statement 1, the validity of capital asset pricing model is equivalent to the market portfolio being mean variance efficient with respect to all investment opportunities. Without observing all investment opportunities, it is not possible to test whether this portfolio or indeed any portfolio is mean variance efficient. Consequently, it is not possible to tell whether capital asset pricing model is right or wrong. This is very serious critique. Anyway, this is appendix. This is a solution for mean variance frontier. So problem. So it's basically this page and this page and this page and this page gives you formula for mean variance frontier. Okay. Start with the vector of asset return R denoted by E, the vector of mean returns, and then E is therefore E expectation R. And denote the sigma S variance covariance matrix or variance covariance matrix. Covariance matrix is same to variance covariance matrix. By the definition, it is E prime. A portfolio is defined by its weight W on the initial securities LSF. The portfolio return is therefore W prime R, where the weight should be summed to 1. Now the problem becomes choose a portfolio to minimize variance for a given mean. Well, that is what we want to do. So to express mathematically, what we want to do is to minimize this variance, conditional on that, well, our target return, conditional on our target return, subject to our target return, and portfolio should be summed to 1. We don't put our additional money in the portfolio. So, but this one is easy to solve. So we want to minimize. So it is an objective function and these two constraints. Given these two constraints, we want to minimize this one. And actually there is solution. Solution is let A is E. Again, E is the expected value. E prime precision matrix, inverse of covariance matrix. E and B is the E prime precision 1. 1 here, 1 is a vector of 1. 1, 1, 1, 1, 1. Okay, and C is 1 prime precision matrix 1, and the variance then for a given mean portfolio, so it is target return. Given target return, the minimum variance portfolio we can achieve is this one. The minimum is this one. Okay, this one is formed by, and how to achieve this one? So it is the best we can do. Or given this target return, we want variance as small as possible, and this is the best we can do. This is minimum portfolio variance. Then how to achieve this? Simple. We can simply hold this portfolio weight. So if we have this portfolio weight, we have this variance and we have this mean. Okay. Well, I want different target. If you need different target return, you can simply change this one, and you can simply plug different number over here. Then you have different variance and different portfolio weight. So thing is that if you change this one, you get different value of this one. You change this one and different this one, right? Then if you draw the graph, right? Look at this. It is a sigma square, and it is a quadratic function. We have a square term mu, right? Square term, right? So we have a square term, and it is a sigma square. Therefore, that's why our efficient frontier looks like this one. That's why our efficient frontier looks like this one. Because it's quadratic function of mu, right? It is mu over here, right? It is a quadratic function. Because we have a square term, over here. We have a square term over here. We have a square term. Usually we have this graph, right? But now this axis becomes y in high school math. We have axis over here. It looks like this one, but now axis is y axis. We'll just rotate the graph. And therefore, the relation between variance this one becomes this one, right? That's we have like a quadratic hyperbola function. So because we have a formula, once you have target return and you have asset, once you calculate expected return as covariance matrix, you can easily calculate optimal portfolio. Well, this is a derivation proof. How? Well, this is the answer. Then maybe you ask why. Why solution looks like this? Well, in order to derive the solution, you have to use some technique called Lagrange multiplier. If you want to learn Lagrange multiplier, you can take my mathematical economics class, or you can go to the economics department and you can take mathematical economics or introductory mathematics for economist classes. Then those economic department or my mathematical economics class will teach this Lagrange multiplier. Or you can go to like 산업공학과 or operation research, engineering management department. You can go to this department and you can learn Lagrange multiplier. Once you learn Lagrange multiplier, it is straightforward to solve this one.